So, welcome back. In this video, we'll extend the concept of partial derivatives a little and formally define directional derivatives. You've already seen functions defined along an arbitrary line. We did not restrict this concept to the coordinate directions. So the idea of just using these for derivatives is somewhat arbitrary. And of course, you can also define derivatives along any line in any direction. And that is just what we are going to do now. So this is part 13.2, directional derivatives. So again, with partial derivatives, we basically capture a function along a line in axis direction. So that maps the behavior of a function on lines parallel to the axis. And the question is, of course, how about general lines? So how about general line directions? And the answer is we can do this just the same. So let's put down the formal definition. As usual, we start with some set x contained in R to the n. We have a function f with x being the domain that maps to R, and we have a point x star somewhere in the interior of x. And now we also need a direction. So further, let v be in Rn, but not the zero vector. And we also need a domain for our one-dimensional function. Usually not the whole line is contained in the set x. We somehow skipped over that step before with the partial derivatives, but let me make this explicit now. So further, let delta be a positive number such that the delta neighborhood around x star is contained in the set x. So in particular, any line through x star is contained in x as long as we do not leave that delta neighborhood. Okay, then we can define the function g. Then define a function g that will be defined on the interval from minus delta to delta and map to R. And we define this by setting g of lambda equals f of x star plus lambda v. So as before, it's just that the direction v is now arbitrary. And if g is differentiable at lambda equals 0, then we call the derivative at 0 the directional derivative of f at x star in direction v. So g prime of 0 is called the directional derivative of f at x star in direction v. And we'll denote that by g prime of 0 is equal to, we'll either write this as d index v f at x star, or as nabla index v f at x star. So that's the directional derivative in v direction. Okay, the definition is straightforward once you're used to this idea of partial functions, functions along a line. So let's have a look at an example right away. So now we know how to take derivatives of functions in all possible directions. And we have already seen a function when we discussed continuity that behaved nicely along all directions, but still was not continuous. So we'll revisit that function now and see if it also behaves nicely with respect to directional derivatives, or if that concept reveals a little more about the function. So we consider a function f defined on R2, mapping to R, defined as either x1 squared x2 divided by x1 to the 4th plus x2 squared for all values of x that are not 0, 0. And we'll just say it is 0 otherwise. So if x is 0, 0. Yeah, and again, see the continuity discussion. We've seen that example there already. Remember, f is not continuous at 0, so we would expect it to also not behave nicely with respect to differentiation. But it is continuous along each line through 0. So it might still be nice with respect to differentiation along lines. So recall, f is not continuous at x equals 0, but it is continuous along each line through 0. So we're going to see how f behaves with respect to directional derivatives through 0. So how does f behave with respect to directional derivatives at 0, 0 then? Okay, so let's consider an arbitrary direction. Let v be v1, v2, and we don't want that to be 0, otherwise it's not the direction. And then we can define our function g of lambda. That is then just f of 0, 0 plus lambda v1, v2. So that's simply f of lambda v1, lambda v2. Okay, if we use the definition of f, then that means what we get is, let's go back a little, so it's x1 squared x2. So that means we get lambda squared v1 squared times lambda v2. And we'll divide this by x1 to the fourth plus x2 squared. So that's lambda to the fourth v1 to the fourth plus lambda squared v2 squared. So we can simplify this a little. Let's see, we have 3 lambdas in the numerator. We have 2 lambdas in the denominator. So those cancel out. There's 1 lambda left in the numerator. We cannot cancel out v1, v2. So we have v1 squared v2. And in the denominator we have lambda squared v1 to the fourth plus v2 squared. So this is true, of course, as long as lambda is not 0. Otherwise, we're at the point f of 0, 0, and the definition is different there. So we'll have to also see what 0 is about. So g of 0, well, that simply is f of 0, 0, and that by definition is 0. Okay, what does that mean for the derivative? Well, let's have a look. See, what we want is we want to compute the limit. We want to know about the limit of g of lambda minus g of 0 over lambda minus 0, because we want the derivative of g at 0. So we need to consider this here, and this is simply the same thing as v1 squared v2 over lambda squared v1 to the fourth plus v2 squared. Okay, so if we let lambda go to 0, there's only this lambda expression here. We'll have to make a little case distinction here. We'll have to consider the cases that v2 is 0 and v2 is not 0. So what happens if v2 is 0? Well, then the numerator is 0. The denominator is lambda squared v1 to the fourth. So that's 0 through whatever expression. And we get a 0. And if we choose not 0, then we can have lambda go to 0. We'll do this in the next step. If we choose not 0, then we just keep that expression here. For v2 not 0. And then we let lambda tend to 0. Well, what happens is, of course, we keep the 0 here. And in the second case, this first expression here, this one here tends to 0. So we simply get v1 squared v2 over v2 squared. Or, if we cancel out the v2, then we get v1 squared over v2 for v2 is not 0. Okay, so that means the limit of this actually exists for all possible v that are not 0, 0. And that means all directional derivatives actually exist. So the limit of g lambda minus g0 over lambda minus 0 for lambda to 0 exists for all v in R to the n with the exception of the 0 vector. And that means all directional derivatives of f at 0, 0 exist. So that function is directionally differentiable in all directions. Okay, so we basically get the same phenomenon as we know for continuity already. Even if we consider all possible directions, this does not suffice to capture the behavior of the function sufficiently. Okay, so even considering all possible directions is not sufficient to capture the behavior of the function. So again, we need a more involved concept for that, and we're going to introduce just that concept in one of the coming videos. Thanks for your attention today.